For this episode, let's talk about how the human ear is able to hear, as well as what this whole decibel system is about. First off, inside your ear, yes, it's separated into three separate regions. One interesting thing to note about this is that your outer ear, which starts from your earlobe all the way up until your eardrum, it more or less behaves as a first order resonance column, right? Closed air resonance column. And we'll do the math to prove that that's, the outcome of it, okay? And yes, inside your ear, in the middle ear, there are these three bones, and the whole purpose of the bones is to amplify the sound signal by as much as around 100 times. Then the amplified signal then goes into the fluid that's in your cochlea, and in there are little fibers of hair, and when the hairs bend, they send an electrical signal to your brain, and your brain processes it. Here's a brief little video just to show you what I'm talking about.
Imagine that we could unwind the cochlea and watch what happens inside when there is a sound. Vibrations are transmitted from the eardrum to the tiny bones of the inner ear. The stirrup strikes the oval window, creating pressure waves in the cochlear fluid and vibrating the membranes between the cochlea's chambers. This vibration is the key to the perception of sound. In cross-section, you can see that the cochlea consists of three fluid-filled compartments. The sound receptors are located in a region called the organ of Corti. The organ of Corti sits atop one membrane and is covered by another membrane. When pressure waves move the lower membrane up and down, hair cells in the organ of Corti bend against the upper membrane. Action potentials arise, and messages travel along the auditory nerve to the brain.
I think one of the most interesting things about how we hear is that our cochlea is really a spectrum analyzer. In other words, there's regions of your cochlea that's hypersensitive to certain frequencies and less sensitive to the rest. All right, for example, the diagram that you see up above, the region of your cochlea that's closest to where all your eardrums are, they're the ones that are responsible for hearing higher end frequencies. And as you uncoil it and you go all the way to the end, the lower end bass frequencies are picked up from the most inner part of your cochlea. That's why whenever they have any of those implants, the cochlear implants, they have to end up stimulating different regions of the cochlea. All right, and they'll have as many as 22 channels to be able to tickle those sensors to give your brain that response of what frequencies are currently available in what you're listening to. So it's pretty interesting that, yes, we are listening to everything as a spectrum analyzer. You know, the thing where they have that graph where, your bass frequencies, if they're there, they'll pump up over there. And if you have some treble hi-hats, then you'll pick up the signals over there. That's what I mean by spectrum analyzer. All right, so there's different regions where it's sensitive to different frequencies, and all those signals are transmitted to your brain, and your brain's able to take it, process it, decode it, and know what you're listening to. Okay, another thing about the way how we listen is that it's not completely uniform. If you recall in an earlier recording, I made a recording where it started off at a very low frequency at around 20 hertz, and it went all the way up to 20 kilohertz. And during the entire recording, I did not change the amplitude of the sound. Now, depending upon your speakers, it may not uniformly send out the signals all the same intensity, but this is one thing that's true with regards to any speaker. The sound suddenly gets louder and louder and louder, and at some point where it hurts your ear, right over here, it's very loud and annoying. And then beyond that, the intensity decreases. Okay, and no, it's not an optical illusion, and your equipment is working properly. The thing is that your ear has a resonant frequency, and as you can probably guess by looking at this, it's somewhere around 3 kilohertz. So let's go through the math behind this. Okay, if I rewind slightly back right over here, if you measure out the length of an outer ear, it's somewhere in the ballpark of roughly 2.8 to 2.9 centimeters. Okay, and again, it's behaving as a first order closed air column. So it's going to abide by this formula over here, 2n minus 1 over 4 lambda, where your n will be replaced with the number 1. That gives us a quarter wavelength for that length of 2.8 centimeters. So if you work out the lambda for this, 2.8, some textbooks say 2.9 times 4 will give you 0.112 meters. Given that the air temperature is around, 25 degrees Celsius, let's say, so we do 343.1 plus 0.606 times, let's say, 25 degrees Celsius, and we have an airspeed of roughly, I'm just going to use this approximate value, of 350 meters per second. Okay, and that's approximate air temperature in a room. So if V is equal to F lambda, then the apparent frequency that is most prominent in your ear, because it's going to resonate the most, is going to be equal to, whoops, V equals F lambda, then F is equal to V divided by lambda. So 350 meters per second-ish divided by 0.112 meters will give you around 3 kilohertz. Okay, and that explains why when you take a look at the spectrum of how your ears are able to hear, we're hypersensitive at that frequency. It's just the natural behavior of just by the size of our ear. Okay, that's pretty neat. And with regards to how sound propagates, like for example, from my mouth, you'll notice that as you stand further away from me, the sound intensity decreases. And you know what? I don't have to move very much. And yeah, it is decreasing, but you won't really notice it. And that's because I'm not moving that much of a distance. And on top of that, your ears, they're not really adjusted towards small changes in sound intensity. They need to be a big change, like 10 times quieter, then you'll notice it. Or at the very least, half the original intensity. That you'll be able to pick up. But if it only decreases by a small amount, your ears really won't pick it up. Remember that as sound travels, it travels kind of like a bubble, right? With regards to the longitudinal wave. So it's spreading out over a larger and larger area. So when you take care of the surface area of this big bubble, that's equal to 4 pi r squared. And yes, volume is equal to 4 over 3 pi r cubed if you need it as a reference, but we're using this formula here. And by definition, the intensity of sound wave is this power over this surface area. So I is equal to P over A. All right. So then therefore, and let me just derive an equation over here. I is equal to the power over 4 pi r squared. Do I have that listed here? Not necessarily. Okay. But often what we do is we just compare the intensity. So in other words, we're going to take the formula and we're going to divide the formula by itself. Okay. So all the values up on top are number 2's, and the values down below are number 1's. And we're assuming that we're in a setup where the noise disturbance, the power doesn't change. So P1 is equal to P2. Therefore, these values, they divide each other out. The quarter divides out with the quarter. Pi divides out with pi. So you get I2 over I1 is equal to 1 over R2 squared all over 1 over R1 squared. In other words, I2 over I1 is equal to 1 over R2 squared times the reciprocal of R1 squared over R2 squared. Whoops, R1 squared over 1. Okay, therefore, I2 over I1 is equal to R1 squared over R2 squared. I'm just showing you the derivation of this formula right over here. That's where it comes from. And I think the big key idea here is just noting that there is this inverse square correlation between the intensity of sound and how far you are away. Okay, it's not inverse proportion, it's inverse squared, meaning that the further you move away, the intensity drops quite significantly. Okay, so the curve is kind of like that with the gravitational curve. Okay, now with small differences in change, you're not going to notice much of a difference, but if you move far away enough, the intensity will drop very significantly. Okay. And here's just one of the consequences of just how we hear things, okay? Imagine if we're in a classroom, right? So you're sitting in the back seat because you like to be that backseat student, and I'm all the way at the front. So we're about 10 meters away. I decide to slowly creep up closer to you because you're sleeping on the table, right? And I only move about 3 meters closer. In other words, I'm starting from my desk, and I'm probably at the very first row if there are 4 rows in the classroom. All right. How much will that change in the intensity of your ears? And the reality is you'll probably not notice me creeping up closer to you. Let's do the math just to prove that out. Okay. So I initially start off at 10 meters away from you, and now I'm approaching 2.93 meters closer. In other words, I'm now 7 meters away from you. Okay. So I'm only about 30% closer to you. I sub those values into this formula here. Okay. So I have R1 of 10 meters, and I have an R2 of 7.07 meters. 10 squared is 100. 7 squared is 49-ish, which is close enough to 50. And you'll notice that, 10 over 49, when you calculate out, or 100 over 49, it's about 2 times louder. So in other words, by me coming 30% closer to you, the intensity does double. Will you really notice it? If you weren't paying attention, you might not notice it at all. Okay, and that's why whenever we deal with measuring sound intensity, we care about big changes. Okay, so we don't often measure the intensity of sound, in this case over here, in watts per meter squared. Right? If you look at the previous formula, if intensity is measured in power, which is in watts, and area surface area, then yeah, technically speaking, sound is measured in watts per meter squared. Okay, so that's one way of measuring it, but often we measure it using another system called the decibel system. Okay, but before we get to the decibel system, let's just go through this sample case study. Let's say you rewind back to the 1960s and you decided to, get your first job working at your first burger joint. Okay, and you get paid $1 an hour. That's pretty much the price that's pretty much the wage back in those days. Your boss likes what you're doing, so your boss says, "Hey, I like what you're doing, so I'm going to pay you an extra dollar more." Back then, you would jump for joy. And the reason why you jump up for joy is because your salary has now doubled. That is a big deal. Okay. And you probably want to have that in your records. Now, if your boss increases from $1 an hour to $2.02 per hour, yeah, it's still double the salary. You'd still be happy, but you wouldn't really care much about the 2 cents. Let's say we decide to fast forward now, another 50 years. So now your grandchildren, possibly even your great grandchildren, are now doing the same job at their burger joint because that's their first job. Okay. And then their boss says, at first when they were working, they were getting paid $1 million per hour. Okay, because of inflation, let's say. Okay, so then it's normal for someone working there to get paid that much. And their boss says, you know what, you're doing such a great job. I'm going to give you a raise. Just like your great-great-grandparents, I'm going to give you a raise by a whole dollar. Would your great-great-grandchildren care about that raise by then? And you'll notice that, between $1 million versus $1 million you wouldn't care much about that by then. Okay, so that increase by a dollar mattered so much more when your values were very low because now you have double the salary. Meanwhile, with very big numbers, that increase in a dollar doesn't matter anymore. It doesn't really impact our final result. And the logarithmic system takes care of that. Okay, so it shows very small numbers very clearly and it matters, but very big numbers are just approximations at the end of the day. And that's all you care about. Okay, so what is the logarithmic scale? Well, here is logarithmic graph paper. It does exist, all right? It's a weird scale. Normally you're used to, if this was 1, then here it would be 2, here it would be 3, 4, 5, 6, and 7. But with the logarithmic scale, every time that you increment up to the next major grid division, you're increasing by 10 times the previous grid division. So you can see how big it grows over here. Okay, and now let's start to talk about the benefits of this type of scale over here by going to a linear scale at first. Let's say we had a linear scale that looked like this, okay, from 0 all the way up to 60. And we need to describe all these numbers over here. Can we show the number 1? Yeah, the number 1 would probably be right over here. In fact, I'll just write down 1. Okay, 2 can be described on the scale. 7, yeah, you could show 7 on the scale. 45, yeah, 45 would be somewhere right over here. Could we show 70? Well, that's where, unfortunately, this scale will fall apart. We need to erase everything and rescale everything. Can you show the number 1 over here? We know the number 1 is somewhere over here. Can we show the number 2? It's probably the next slash beside it, so it's going to be hard to see the differences. Even though going from 1 to 2 is a big deal, you won't see it anymore. Just like 1 to 7, you probably can't see it very well on that scale. 45 can be roughly approximated somewhere over here. 70 can be approximated somewhere over here. 300 over here. Uh-oh, we can't show 20,000. That doesn't work on this scale. So now we got to erase our scale and go with another scale. And you can probably see the problem about this. Okay, unfortunately, with a linear scale, you lose out on the details with the small numbers, and the big numbers are approximations anyways. So let's say that we did this all logarithmic instead with the scale that's provided over here. If you want to show the number 1, number 1 can be clearly shown here. If you want to show the number 2, believe it or not, this tick over here represents the number 2. Just like 3, 4, 5, 6. So if we need to show number 7, that's where we dot it on the line. If we need to dot 45, well, we know that it's 20 over here. That's 30, 40. So 45 would be some number which would be somewhere over here. It actually scales towards about 70%, all right, towards the end. But 45 can be faithfully shown on the scale. 70 can also be shown. 100, 90, 80, there's 70, okay? So you can see that we can show all these numbers. We can show the number 1, we can show the number 2, we can show the number 7, 45, we can also show the number 70 as well. What's the next one? Oh, 300? No big deal. 100, 200, we can show 300 very faithfully. We can also show the number 20,000 very faithfully as well. There's 20,000. 500,000? Oh yeah, it fits on this. 1, 2, 3, 4. There's 500,000. And that's the benefit of a logarithmic scale. It's able to show all the small details if you need it to show it, and big numbers are going to be approximations anyways. You're not going to care, like, for example, if a condo goes for 510,000 versus 500,000. If you had that kind of money, $500,000 lying around, you'd buy it anyways. All right, so you don't care about that extra $10,000 in difference. Okay. Meanwhile, if you want to show $10,000, yeah, you can show $10,000 in the scale as well. It will show up. All right, so it can show details of very small numbers very well. And big numbers, you're going to approximate anyways. $1 million home is $1 million, even if it's at 110. It's still $1 million home. Do you want to describe a $2 million home? You probably could, and it'll probably be a marking somewhere right over here if I had that on the scale. And I only had to make it just about this much larger on the graph just to show numbers that are 200 million, 300 million, 400 million, all the way up to 10 million. Okay, so that's what logarithmic graphs do. Expand out numbers down below, compress numbers up big, up high. When you deal with sound, it's based upon this logarithmic scale, okay? So it can describe very small intensities. It can also describe very large intensities using just two significant figures. There is a formula for it. As the name implies, if it's called decibel, it means to multiply by 10. So there is such thing as a bell system. It's just that with bell, you deal with decimal numbers, and as they don't want to deal with decimal numbers here, we just want big whole integers to approximate things with. We call it decibel. And here's how it works out. Okay, we have a formula that looks like this. Beta for the decibel intensity is equal to 10 times the log of base 10 of I2 over I1. If you want to drop the number 10 listed over here, you could, and that's perfectly fine as well. It's implied that it's base 10 if you don't write it. And what you do with this formula here is that you're going to divide the intensities to tell the reader that this is how much louder you want it to be. Okay, so let's say that you go from 1 watt per meter squared to 2 watts per meter squared. Yes, in real life, your eardrums will be blown out with these numbers here, but I'm using large numbers just for comparative analysis. You're just going from 1 to 2. Okay, so originally you had 1 apple. Now you have 2 apples. How much bigger is it in the decibel world? In your calculator, you would type out 10 times the log of 2 over 1. So you take out your trusty calculator, and you do 10 times the log of 2 over 1. And your calculator will always show this number here, 3. So this is the general assumption here, okay? Anytime that you double an intensity, you're going to increase by, in the decibel system, by a gain of plus 3 dB. Now let's try it out for all these numbers here, okay? So from 1 to 10. So I'm going to take this and I'm going to replace 2 with the number 10. And it's going to increase up to 10 dB gain, and that is true. The common misconception that students have is that when you go from 1 to 10 versus 1 to 100, that you go up by 100 decibels. But remember, the decibel system starts squishing the large numbers. So it's not going to increase by much when you deal with larger values. Okay, so if I reverse back and I type in the number 0 over here, so now I'm doing a log of, I'm starting from 1 apple. Now I have a huge bag of 100 apples. My gain goes up to 20 dB. And if I go from 1 apple up to 1,000 apples, again, that sounds like a big amount, but in a dB scale, they just like to squish it down. Okay, so you're taking this and you're doing 1,000 to 1. You'll increase up by 30 decibels. In fact, the secret life hack here is that anytime that you have, multiples starting with a 1, all right, so 10, 100, 1,000, so on and so forth, all you need to do is just count the number of zeros. So 1 0 is a 10 decibel gain. 2 zeros is a 20 decibel gain. 3 zeros is a 30 decibel gain. So when you go from 1 to 1,000,000, well, there are 6 zeros over here, so that's a plus 60 dB gain. All right. So in the future, if you ever say that you need to increase something by 60 dBs, that means you want to increase it by around 1,000,000 times. Well, what if you don't want to increase, but you want to decrease? Let's say you start off with 1, but you only want half. Well, you take out your calculator, and now we're going to edit this part over here. So we start off with 1, and now we're going to drop down to half of it. Or you could just type it out as 0.5 divided by 1. It'll give you the same answer. Okay. You'll notice that you drop by negative 3 dB. Now, on your calculator, yes, it's going to say negative 3.01029957. But as I said, with dB, we don't care about those minuscule details. All right. We want just the big picture. So dB scale is one that we seldomly ever deal with decibels. Yes, if you have a sound intensity meter, it may show it to just 1 decimal place, but that's it. We don't really care about those small, minuscule details. All right, so anytime you cut down by half, it's approximately -3 dB loss. What if you go down from 1 down to 0.1? Well, really, on your calculator, you're going down to a tenth, right? So you're starting off with 1, and now you're down to a tenth of your original value. And you'll see it goes down by -10 dB. All right, so let's summarize these key ideas here. Anytime that you gain by 3 dB, that means your value has doubled. Anytime you gain by 10 dB, multiply by 10. Okay. Any loss of 3 dB means that your intensity is cut in half, and a loss of 10 dB means that you're going down to a tenth. And let's just practice through a few examples. Okay. For example, let's say that you increase by 10 times. You know that translates into a plus 10 dB. If you increase up by 100 times, well, that's 10 dB plus 10 dB, right? Which will give you your plus 20 dB. Because 20 dB is effectively equal to 10 dB, which is that you're multiplying by 10 times, and you're adding another 10 decibels on top. And that's the interesting thing about the decibel system. You add in the decibel system, but you multiply in the linear world, because times 100 is really 10 times 10. That gives you times 100. So the dB world you add, the linear world you multiply. And that's the life hack that they use to use this instrument over here. Don't know if you guys have ever seen this before, but this is called a slide rule. It's an amazing machine that can add, subtract, multiply, and divide. And if it's all decked out like this version over here, it can do SOHCAHTOA for you as well. All right, so this is the fully loaded edition that can take care of that. But it does all this magic using the logarithmic scale. Under that pretense that in a logarithmic scale, if you add on it in the linear world, you're multiplying and dividing. And this is able to multiply and divide using that little life hack. I'll show how to use that in a future episode. Right now, let's just stick with the stuff over here. All right. So if you increase your intensity by, let's say, 1,000 times, as I said, out of sheer laziness, just count the number of zeros. That's plus 30 dB. Well, what if you decided to amplify by, let's say, times 20 times? Well, that's effectively multiplying by 2 and then multiplying by 10 yet again to get to 20. In the logarithmic world, you're effectively doing 10 decibels, and anytime you double, you're going to add another 3 decibels. So in other words, if you gain by plus 13 dB, you're effectively multiplying by 20 times. Okay, so that's one of the benefits of the decibel system. It approximates things, and if you remember these rules up here, you can do all of your logarithmic calculations mentally in your head. All right, for example, if you want to amplify by 4 times, then it's really just times 2 times another 2. Or a 3 dB gain plus another 3 dB gain. In other words, you're gaining by plus 6 dB. Okay, so plus 6 dB means that you're multiplying it by 4 times gain. That's what it translates into. Okay, now if you're not comfortable doing this in your head, you can use the formulas. The formulas will work out. For example, how many times greater is an intensity of 19 decibels? Well, we just argued right now that 20 decibels is the same thing as 10 dB plus 10 dB. In other words, times 10 with another 10. In other words, you're roughly talking about approximately 100 times amplification when you're at 19, right? You're going to be less than 100. You're going to be some number. And in fact, you can probably approximate the number out in your head if you already knew the answer, right? For example, I already know that's going to be somewhere around 80. Let's do the calculations to see if we're close to 80 or not. Okay, so your beta is equal to 19 dB. Here's the formula, but now we're subbing in the 19 right over here. All right, and we need to isolate for I2 over I1. In other words, we need to take the formula and we need to swap it around. Again, anytime you're solving problems, you're always doing the opposite process. Whenever you're solving an equation, if you notice that it's added on one end, you're going to subtract when you bring it to the other end. If it's multiplied on one side, you divide both sides by 2, right? So that's what we're going to do here first. We see that the 10 is multiplied by log. So to get rid of the 10, we need to divide both sides by 10. There we have it, beta over 10. I just did a quick swap Rooney here. Okay, so here's the equation swapped around, and here's the equation divided by 10 on both sides. What's the opposite process of log? Well, if you've ever seen the log button in your calculator, usually the opposite process is when you do shift that button. And if you look carefully, what you need to do the opposite of log is that you bring both sides to the power of 10. And that's literally what you do. You bring both sides to the 10. And 10 to the power of log, really those two, because they're opposite processes, they cancel each other out. So you're left with I2 over I1, is equal to 10 to the power of beta over 10. So that's how you would rearrange this equation. And now you can sub in the 19 over 10, and I already knew the answer. That's going to be around 80 on the calculator. It'll give you, what is it, 77.9, I believe. 10 to the power of 1.9, because 19 over 10 gives you 1.9. And yeah, I get 79.43. Close enough to 80. As I said, with the logarithmic system, if you're off by a little bit, it's okay. You still got 80-ish, right? 79 and 80, that's a little bit more than 1% error, but that's good enough, and that's why the DB system works. And yeah, you could do it in your head. If you're wondering how in the world did I was able to do this in my head, well, I knew that to get to the number 19, all I'm doing is 10 plus 3 plus 3 plus 3, at least in the DB world. Okay, again, in the DB world, you would add, but in the linear world, you would multiply. So 10 dB means you multiply by 10, 3 dB means you multiply by 2, another 3 dB means you multiply by yet another 2, and yet by another 2. So 10 times 2 times 2 times 2 gives you roughly times 80-ish. And that's our answer over here. Okay, so a logarithmic approach is another way to deal with multiplication and division without actually multiplying or dividing. It does work out as long as you memorize these basic key ideas here. Okay, positive, you're multiplying, minus, you're dividing. And yeah, many audio editing programs rely upon this. So if you ever used a mixer before, like this virtual mixer here, if you normalize everything at 0 dB, what you're saying is that you want the audio recording to be at unity. In other words, whatever the input is, the output is at the same exact value. And if you don't hit it spot on as an audio mixer or audio engineer, the human ear can't notice the difference, all right? So these values over here, I'm trying to get close to 0, and these are probably good enough. And even if you move it by a slight bit, your ear, unless you're really, really well trained, you're not going to notice that nuance. However, if you find out for example, the background singer is singing too loud and you want it to be at half the intensity, if this is the lead singer, then the background singer needs to be dropped down by -3 dB. That way, that background singer will be at a quarter of the intensity. And let's say you want the choir to only be at, half for -3 dB, and you want the choir to be at quarter of the initial value, then you'll drop down to -6-ish dB, somewhere around there, and it'll be good enough. If the drums are 10 times too loud, you'll drop it down to -10 dB. Okay, and if you have some other percussive instrument that's just way too loud and you want to drop it down to 1/100th of its original value, then yeah, you'll drop it down to -20 dB. Now down to 1/100th. Okay, and if you want the fireworks to be dropped down, by 1,000 times, -30 dB. And that's why when you decrease these things, they kind of just skip through numbers, right? You're already at 50 over here because when you're at -50 dB, now you're at 100,000 times quieter. -60, you're in 1,000,000 times, right? -70, you're at 10 million times. -80, well, at -80, you're at 100 million times. And by then, it's like you're almost at nothing. And that's why after the 80 or 90, it kind of just says, forget it. Just call it negative infinity because no one's going to be able to hear it anyways. You already know that at -60 dB, you're at 1,000,000th of the original sound. So imagine me talking right now, cutting in half, but cutting it down to 1,000,000th. You're barely going to hear it anyways at -60 dB. Maybe the hum and noise in the background, yes, but that's about it. Okay, so that's why even audio engineers, they use this system over here because you care about the changes at the beginning. If you want the lead singer to be twice as loud, then yeah, +3 dB. If you want the lead singer to be 4 times as loud, +6 dB. Or if you need the lead singer or another lead singer to be 10 times louder, then yeah, +10 dB, and it kind of stops over there. Because if you make it, more than 10 times as loud, you're going to clip, and then it's going to sound distorted. Apparently, the Magic microphone sounds like that. Magic mic, sure. Okay, relating decibels to sound. Most people think that, decibels is this scale that I have right over here, and that's true. Okay, so in other words, a conversation I'm having you right now, if you're with me, it's roughly at 60 dB. But where did they get this number 60 from? A decibel scale system is one where it's referenced to something. And you know that 60 means 1,000,000 times louder. 1,000,000 times louder in reference to what? Whatever that's at 0 dB. Because 0 dB is the lowest sound that a human being can hear, and it can be approximated at 1 times 10 to the -12 watts per meter squared. That's our reference value. If you want an analogy for it, it's kind of like a pin dropping in a stack of hay about 1 meter away from you. That's 0 dB. So if you have 10 pins, yeah, it's going to sound like 10 decibels. If you have 100 pins, yeah, that's probably the sound that a whisper at a 1 meter will make. And so on and so forth. You can imagine the stories, you keep on going, all right? So you start off with 10 pins, 100 pins, 1,000 pins, and you just keep on going. And that's how the decibel system works. Okay, so your reference value is at 1 times 10 to the negative 12, and you're going to sub it in for the value of I1. In other words, if you rearrange the equation, then yeah, you could write it out like this as well. The intensity of sound, or I2, is equal to your reference value times 10 to the power of beta over 10. And it will mathematically work out. Okay, and as described many times, the decibel system is beneficial because you don't need to multiply anymore. You're just adding. And let's just go through some quick examples over here. Okay, let's say that you need to magnify something up by 40 times in total. So you're going to first amplify by 2, amplify by 10, amplify by 2 to get to 40. In a decibel world, we know that doubling something is adding by 3 dB. Increasing by 10 times, you're adding by another 10 dB. Doubling it again, you're going to add by another 3 dB. So 3 plus 10 plus 3 will give you plus 16 dB. And you can try it out. You can do 10 times the log of something that which is 40 times louder than what it was before. All right, pull out your calculator. 10 times the log of something that's 40 times bigger than what it was initially. What will it look like in the dB answer? Boom, 16. No calculator needed because of our rationale that we know that double is 3 dB, quadruple would be 3 dB plus 3 dB. Add another 10 dB there, and you're there perfectly. No calculator needed. Okay, so let's say that somebody's whispering at 27 decibels, and then you put a megaphone in front of them, and that megaphone is able to increase the sound by 10 times. What will be equivalent in the dB world? One thing you can do is you can convert dB into a sound intensity, multiply that by 10, and then convert it back into dB again. But it's a big waste of time because in the dB world, if you want something 10 times louder, just add 10 to it. 27 plus 10 gives you 37. Done. No calculator needed. Okay, let's say that it's a sound that's already at 27 dB. It's too loud. You need to cut it by half. What you going to do? Are you going to drop it down to 13 dB? Or are you going to drop it down to 24 dB? Take your pick. Put your finger on the left side of the screen or on the right side of the screen. Now remember, if you're trying to half the intensity, you're decreasing it by 3 dB. So you're going to take 27 and you're just going to subtract 3, and 24 dB is the correct answer. Right? So for more fun adventures in the world of dB and how it works, get started on your homework, and I'll catch you in the next episode. Bye for now.